Okay, good afternoon. Welcome back to the afternoon session of ICCP 2026. So we have the next session, scene representation and editing. But before that, just a few announcements. So for the authors, feel free to grab all the posters outside, and then they are by the registration desk. So feel free to grab them if you want. Okay, so we have one invited speaker talk today here. Computational light field synthesis for high resolution 3D display and printing. So we have the speaker here, Seung-Won Kim from Tsinghua University. Let's welcome.
Good morning, everyone. My name is Seung-Won Kim. I'm coming from Tsinghua University. Original speaker of this talk is Jiamin Woo, but due to the visa issue, he couldn't come to America. So I am Professor Jiamin Woo. We both belong to Professor Dai's group. But my research topic is a little bit far away. Today I'm going to introduce our group's two recent works. One is sub-second super fast volumetric 3D printing, and another one is a 3D display with a ultra-wide angle view. 3D printing techniques are very similar to imaging technology. So point by point 3D printing is very similar to confocal imaging, and layer by layer 3D printing is very similar to light sheet imaging. And volumetric 3D printing is very similar to CT, computational tomography. And CAL is one of the most well-known volumetric 3D printing methods, computed axial lithography. Here, our group is recently, for 10 years, our group is focusing on scanning light field microscope. We are focusing on some in vivo mouse imaging, but we have plenty of experience on light field imaging. So we challenged it to fabricate some new system for 3D volumetric imaging using light field illumination. Previous CAL, computed axial lithography, has some limitation because it needs some time. So the solution should have very high viscosity. Otherwise, the 3D object, 3D structure can be going down due to the gravity. So we focused on this point. So we try to make a very ultra fast 3D volumetric 3D printing system. And another issue is the non-uniformity of the focal resolution for CAL. So due to the limited focal depth, so the resolution across the field of the 3D printing volume is not very uniform. So we focus these 2 points. And so this is the idea of our concept. So we place the DMD projection in front of the field, and then we attach the periscope module inside the field, and we rotated it very fast. And then we can deliver the 3D volumetric projection to multiple angles. Normally we project for 1,800 angle at the same time within 0.6 seconds. In this way, as you see here video, we shine the light with one circle, then we can generate the 3D printing structure immediately by using the photo cross-linking. And for illumination, we simulated coherent light, incoherent light, and both have some pros and cons. Coherent light showing some higher resolution, but it's not very continuous. And incoherent light showing very continuous illumination. However, the resolution is a little bit lower. So we use the coherent light, and then we integrated it like a incoherent light. Integrate multiple angle as an incoherent light. But problem is to integrate coherent light to incoherent integration. We need to calculate a lot of optimization process. It was the problem because we had to calculate 0.1 billion pixels for each printing. So we changed the algorithm. We developed some algorithm. We named the cost-to-fine optimization strategy. We used the cost optimization using some existing gradient descent algorithm. So we used some existing algorithm first, And then we iteratively increase the resolution step by step. So basically, we optimized using some optimization of the binarization factor G. Here. Here is a cost step. We were able to some low resolution 3D printing first, and then we optimized the holographic illumination step by step. So this is a little bit complicated. So we use the iterative method. We use the loss function and to minimize the error of the holographic illumination. And by optimizing the binarization factor G, we were able to achieve the very high resolution 3D printing structure. And we also increasing number of the projections also contributing to the high resolution imaging at the same time. So we use the 1,800 projection number and use the G10 parameter. And another problem of the holographic stimulation is the refraction due to the air solution interface refraction. So in the air, we can project light as we want, at the point we want. But however, due to the refraction, the beam is refracted, and the resolution is degraded through the propagation in between the air to solution. So to correct this, we place the two cameras in lateral and axial, in front and side, and based on this camera imaging, and we minimize the offset value iteratively, and then we could achieve some well-calibrated 3D printing structure like this. And also we evaluated the resolution across the 3D printing volume. Our 3D printing volume is about 1 centimeter, so 5 millimeter to 5 millimeter from the center focal plane. So even here and here showing some very uniform resolution across the 3D printing volume. However, without our optimization algorithm, so just without using the iterative algorithm, the optimization algorithm, normally the beam resolution at the focal plane is very high. But however, out of focus plane cannot be same as the focal plane. And in summary, we use the cost-to-fine holography optimization to optimize the illumination pattern. For example, conventional methods use some very intuitive pattern, but by using our holographic optimization method, we are able to generate very optimized holographic pattern, and it results the high resolution 3D printing result. And also, we also corrected the aberration in between the air to solution interface refraction, and we achieved almost 11 micrometer precision across the 1 centimeter printing space. This is the result. As you see, we can fabricate the very sharp structure and like this 3D-dimensional structure. And also, we integrated a fluidic device system here, and using this one. So here is 3D printing space, and after printing, we turn on the flow. Then the 3D structure moves to next step. Then we can generate 3D structure like continuously, like this, like a mass production. This is another demonstration. As you see here, we shine the light, and you can see squid is generating over time, right? So illumination time is only 0.6 seconds, but the cross-linking chemical reaction is a little bit require at least 1 second. But it's fast enough, we think. And we also demonstrated during the revision, we have to generate many different types of some 3D printing structures. And we tested multiple some biomaterials. So, for example, mainly we focus on using PGDA because we are targeting this application for biomedical application for the future. And compared to previous method, this work is placed here, is over the trade-off. So in terms of the volume size, volume efficiency, box cell efficiency, and volumetric efficiency, so our work showing very higher box cell efficiency compared to previous method, and higher volumetric efficiency too. And this is a future direction, but it's the next version, so it's not very critical. So another application is we are working on this for the next project. So also using some process solution, we can visualize some 3D-dimensional, some like a real 3D-dimensional process structure like this. So this could be next project. And another topic today is live field display. Actually, yeah, I'm a little bit stuttering because my background is biology actually. So it's a little bit, not familiar for me. So another topic is live field display. And human visual information is around 70 or 80% of our sensory input. Our brain handles a lot of visual information all the time. But visual information have many factors. For example, angle and color, intensity and position, a lot. But however, conventional display is only 2D display. It's very limited information. But live field display can offer human for some very rich information, something like a vector function of position and angle. Looking glass is one of the best well-known commercialized item for 3D display. And it is used for advertising and telemedicine and any other visualization purpose. But compared to 2D display, conventional live field display has the lack of the resolution, and also viewing angle is very narrow. So we try to address these two issues. Our group, almost 10 years ago, our group is working on computational vision a lot, but this day we are focusing on more focusing on some bioimaging. But our group has a lot of information, a lot of experience on computational vision. So this is all our group's previous work, and always there was some bandwidth limitation. So because when we push some resolution, we lose temporal resolution, and we push the angle information, we push some more angle, then we use spatial resolution. So always have to compromise the temporal resolution, spatial resolution, and angular resolution have to be compromised each other. So we are thinking one of the limitation in this field is the lack of high bandwidth product. And so this project is published in Nature Photonics recently, and this display has two critical modules. One is super Snell lens array. It's for super Snell lens array is for a wide angle view, and HMS holistic mount scanning. Holistic mechanical scanning. Yeah. HMS is for high resolution. So super Snell lens, why we use super Snell lens? Because across the different angle, super Snell lens offer very well-focused plane, the focused plane from the display panel. For example, compared to the conventional cylindrical lens, this is a conventional cylindrical lens used for looking glass. As you see, when the angle is changed, the focal plane is also shifted from the display plane. So it induced a lot of aberration. And only using super Snell lens still have some aberration, but super Snell lens with aperture, we can get some very stable focal plane across the up to 75-degree and total the viewing angle can be 150. And HMS is because super snell lens only showing the display pixel something like this. Very limited pixel can be shown to human eye. Then we cannot get high resolution images. So HMS is shifting the super snell lens left and right like this. And then human eye can see some integrated information from the scanning and within 20 milliseconds. So within 50 milliseconds. So total frame rate can be 20 hertz. By combining HMS and super snell lens, another benefit of HMS is HMS means lens and this the acrylated the part is moving together. So if we make only lens moving, then the motion sync error is very severe. So then you can see a lot of aberration. However, using HMS, we can minimize the sync error. And by combining HMS and super snell lens, we were able to get high resolution with a high ultra-wide viewing angle. This is demonstration. This is original image. Without scanning, the image looks like this. But after scanning, you can see some higher resolution image. This is principle. In this, for demonstration, we use the gray and white color mask. But in real situation, we use a black and white color mask. And due to the pixel density change across the with the angle view, so we easily calibrated by normalizing the intensity to the minimum intensity. So by changing the angle, the intensity can be stable like this. It's very simple. And as a result, by combining super snell lens and HMS, we were able to get 8 times higher resolution compared to without scanning, and 150-degree viewing angle like this. Okay. And we also compared with commercialized method, commercialized looking glass. So everything is saying is better. Okay, this is a looking glass result, and this is our method. You can see much more stable angle dependency, and also you can see much higher resolution without artifact, pixel artifact. Okay. This is without HMS. This is with HMS. And also we can play some video too. So frame rate is limited to 20 hertz, but still we can play 3-dimensional video. And this is a real movement of our display. So this is, you can see some part is moving like this. This is super snell lens shifting. You see, we can, by using this method, we can achieve the high resolution and ultra wide field of view. Yeah, this is the end of our talk. Our group has some very different. Our group is working on very different topics: AI, or bioimaging, or neuroscience, or immunology. And this work is also a part of our group's work. We are still working on some computational vision. And our group the number of our group is about 100 people. So. Very big group.
That's a huge lab.
Yeah, it's a minimum actually. It's over the years, the number changes from 100 to 200. So 100 is always a minimum. Yeah. So the biggest advantage of the big group is we have many different topics and all have different topics. So if you want to get some collaboration with some other group, yeah, you don't need to contact the other group. You inside the group already have many. Actually, my working topic is actually neuroinflammation. It's dementia or Alzheimer, but yeah. So very very diverse topic we are working on. And also about the 3D printing and 3D display, you can contact to Ujiami's email. Yeah. Okay, thank you for paying attention.
Thank you so much. So.
Q&A is also okay. Yeah. If there's a Q&A, then.
Yeah, so we have time for maybe one question. A very impressive group, like question over there, yes.
Hi, I was just curious if you're restricted in the colors of resin that you can use for the 3D printing.
Sorry, can I?
Are you restricted to what color resins you can use for the 3D
Oh,
printing?
that's a good question. So actually, I didn't mention that clearly. So here. So this principle is very robust to color. So RGB can be used and has no problem. So, yeah.
I think she means the 3D printing one. The 3D printing
one. 3D printing one.
The color of resin. It's supposed to try, because right now mostly it's transparent, right? So
yeah, it should be, the monomer should be transparent, but depending on the molecular weight of the PGDA, it can be white, it can be transparent. The product can be white or transparent. Yeah, the solution should be transparent.
okay, so we can continue discussion later during the coffee break. Okay, let's thank the speaker again. Thank you so much. So the next talk would be the ICCP paper, Transplat, Instant Object Relighting in Gaussian splatting via Spherical Harmonic Radiance Transfer. The speaker will be Bo-Yang Yu from UCSD. Right, okay. Let's welcome. My bad.
My name is Tony, and I'm from Rice University. And today I'm thrilled to present our newest work, Transplat, which is instant object relighting and Gaussian splatting via spherical harmonic radiance transfer. So there's three key words here: Gaussian splatting, spherical harmonic, and radiance transfer, and I'll cover them individually. Let's first start with Gaussian splatting. I hope everyone has at least heard of this method. It has risen to become a really popular neural rendering method to explicitly represent scenes using these kind of blobs that are made of 3D Gaussians. So think of it as like Lego blocks that you can use to reconstruct any objects that you want explicitly, and then it represents view-dependent color using spherical harmonics. So this has really become a really popular backend or primitive for example, warp models or all these simulators nowadays. But however, unlike mesh-based assets, the source lighting is sort of baked into the spherical harmonic coefficients during training. And if you want to, for example, do insertions of these trained Gaussian representations into target scenes, naive insertions would just look not photorealistic because it would just kind of look like copy-pasted without proper relighting. There are existing methods that relights Gaussian splats. However, all of them pretty much uses inverse rendering method, which decomposes the objects into explicit material properties like albedo, roughness, metallic, which is, in a sense, it is the estimation is ill-posed and also takes a really long time, like over an hour for a single object, and also has a pretty big memory overhead. So what Transplat aims to solve is this slow optimization problem. We want to formulate a really lightweight and approach that would relight existing Gaussian representations into a novel environment in less than a second. So it achieves real-time relighting, and it completely skips the BRDF estimation or material estimation with over 100 FPS and less than 1 GB of VRAM requirement. So let me first kind of touch base on what spherical harmonic is and how it's used in Gaussian splatting. So SH, short for spherical harmonic, serves as the spatial basis function. it essentially compresses a view-dependent color into a small set of trainable coefficients that is optimized during training. And here's a little demo here. The k are the coefficients corresponding to each basis function, and the linear combination of the function weighted by k represent the full radiance distribution of the sphere, where we can efficiently query the color based on any given direction. So in this paper, we make the assumption that within SH, the coefficients within the SH are naturally handles diffuse and specular in different bands. So we have a decomposition here. On the left is just a render using just the DC components of the spherical harmonic. You can see it's mostly like diffuse color. And if we render only using the higher order bands, we see that it's sort of the specular or higher frequency term. And the linear combination of them produces the final combined render. So it is assumption because you can see on the plate on the left, there is still a little bit of a specular highlight that's leaked. However, mostly we can say that it is a diffuse and specular decomposition. And this inspires our downstream radiant transfer decomposition. So transplat has three basic components. It assumes input a pre-trained Gaussian splatting asset with known source and target environment maps or light probes. It performs first self-shadowing and then radiance transfer to relight the object. So I'll first start with how we handle self-shadow. So we handle self-shadowing completely within the SH domain by just shadowing the environment maps. So given the known source and target environment maps, we first compute the visibility per Gaussian, and then we project them in the SH domain to achieve these SH coefficients. Then we use something called a Gaunt tensor, which is just a mathematical tool that allows us to multiply these three SH coefficients in SH domain. So the result of this is we get the shadowed source and target environment maps. So here's the visualization of what's happening. So given this HDRI environment map, we first do SH projection. As you can see, it's sort of a smeared out low frequency representation of the original environment map. And after the Gaunt tensor, it uses the visibility term to shadow the environment map. And here's the visualization. If we do not shadow the instant radiance, there is no self-shadow in the final relight. However, with the shadowing within SH domain, we do see that it produces right here the shadow term that closest resembles the ground truth. So next, I'm going to talk about radiance transfer, and I'll first start with diffuse transfer, which is how we handle relighting for diffuse color. So what is radiance transfer? It is a pretty classical framework from Mahajan's paper that evaluates how the incident lighting becomes the outgoing radiance, reflected radiance, by filtering environmental illumination through an object's surface property. So this relighting requires no pre-simulation. We just need to know the geometry, and we do not need to know any material properties. So one mathematical equation that's fundamental is that we treat the reflected radiance as a material filtering step. So there are three components here. So there is the reflected radiance, the BRDF, which is the material, and as well as the incident radiance, which you can just understand as the environment map. So basically the reflected radiance is the material filtered version of the incident radiance. So in order to find out what the object should look like in the target environment, so aka the reflected radiance of the object in target environment here, we just need to, we can formulate this ratio of like just the division between the reflected radiance of the target and the source, and we see that the BRDF term actually cancels, assuming this is a Lambertian surface, so for diffuse matte surfaces. And you can see that in order to relight this, actually, in the SH domain, all we need to do is swap the coefficients from the incident radiance of the source to incident radiance of the target. So that means that in order to relight for diffuse, all we need to do is scale each or each Gaussian's DC harmonic terms by a simple irradiance ratio. So here we see that here are the two outputs from previous stage, the shadowed target and source environment maps. All we need to do is do a convolution within SH domain with the normals and multiply this calculated irradiance ratio with the out-of-the-box DC band color, and boom, there we instantly get the diffuse relight. So I hope that was straightforward. Now I'm going to talk about how we handle the specular terms. So this is a little more complicated because usually in order to relight any specular object, you would need to estimate the full BRDF or at least some kind of roughness material. So because we don't do that and we want a really lightweight approach, we use essentially a proxy. So remember this equation I talked about, which is the reflected radiance equals the BRDF times the incident radiance. We can sort of calculate a per Gaussian BRDF term by just doing this division. And this is using the band energy within the higher order bands of SH that is already stored and available from the pre-trained Gaussian splats. So this proxy basically tells us how much the material actually attenuates each frequency that the target instant environment is offering. So if we do not do this attenuation, the full relight will kind of look like a mirror. It will just preserve all of the high frequency energy in the target environment, which that is obviously wrong because, for example, the matte part of the leaves needs to stay matte, while the glossy part of the pot should preserve the specular highlights. So we can see that here is kind of like a comparison that when we do this bandwise attenuation, everything stays where it should be. So essentially with all these components, the final relight is just a linear combination of the diffuse and specular contributions. So here's without relight, here's diffuse, and this is specular, and we can see the final relight is just a linear combination of the two, and it closely resembles the GT. So for experiment here, we use across 6 objects in 3 environments. We use primarily the TensorIR dataset, which is a very standard kind of relighting dataset to benchmark. We compare with these 5 baselines, and we can see that even though Transplat is a super lightweight instant approach, it outperforms them in terms of quantitative metrics. And you can see here on the table, it really shows how lightweight we are compared with these baselines, is that just with a 2-second pre-computation, the relighting time much less than 1 second, and a VRAM requirement of less than 0.5 gigabytes, these other methods has some way bigger overhead, and it's just not meant for any real-time application. So here's a demonstration of the spatially varying relight, as well as soft shadow I was talking about. So here we can see that for this object, we can see the actual shadows that it is kind of rotating with the environment, as well as the specular highlight rotating with the kind of rotating environment. So part of Transplat is not, for the trans part, it not only stands for transfers, it also stands for transplanting. So our intended application of our model is that we want to take any object that you want from the existing Gaussian splatting scene, and we want to move it to a target Gaussian splatting scene and achieve sort of instant relighting. So here, for example, from this MIPNERV 360 scene, we can extract this vase object, and we want to insert it and then relight it into this like classroom scene. So without Transplat, if we just bluntly insert this, it looks very unnatural. But however, after Transplat, we see that we have correct shadows as well as proper relighting. Similarly, in this case, we want to insert this bonsai into this kind of like a dining room scene. Transplat just adds the proper soft shadow as well as a lighting that harmonizes this appearance. We also built a dedicated graphic interface for our model for user to try. essentially you can drop assets into new scenes and relight it in real time. So we can sample the environment or the light probe in real time, as well as you can see the lighting is relighted in real time as well. So in conclusion, we are the first radiant transfer relighting method within Gaussian splatting that achieves instant off-the-shelf relighting without any retraining. And I think it's a pretty lightweight and elegant approach compared to conventional baselines. And one takeaway is that we treat the relighting as a frequency domain transformation of the radiant signal rather than just an inverse rendering task involving material estimation. And our code, as well as paper, is available on our website. And I'll take any questions that you guys may have. Thank you.
Thank you. So open for questions.
Hi, thank you for your talk. I was curious, did you validate your relighting conditions with experimental, like actually moving that base into the classroom? And where do you see are the remaining sources of error between those two?
So actually a real life experiment is a little hard to conduct in terms of capturing a real data set because you need to fix the object as well as like estimate a proper lighting. We haven't conducted any sort of real world quantitative or side-by-side comparison yet. We've done that with synthetic blender cases and we achieved pretty high metrics. However, for real light cases, it depends on, for example, first, the HDR environment, your light probe you're capturing, as well as the actual scene lighting. So I mean, like, Jan is going to present his papers about capturing HDR. So maybe in the future we can sort of use that to evaluate an actual real-world comparison.
Cool. Any other questions from the audience? Okay, if no, let's thank the speaker again. Thank you so much. So the next paper, also the last talk of this session, we have like Pandora, casual HDR radiance acquisition of indoor scenes for image-based lighting. So the speaker is Yannick. Let's welcome.
Thank you for the introduction. Give me still 1 second. I'm getting started, warmed up here. Can you see everything is perfect? Hey, thank you so much. Thank you for the introduction. So it is my great pleasure to present you our work. Unfortunately, the first author, Momo, cannot be here today due to visa issues. And it is unfortunate because Momo was really excited about presenting his work. And we started working on his presentation in February, and what's happening in February is the Super Bowl. And Momo was a great fan of the Super Bowl of American football, so he ran into the coffee table of the laboratory and said, I want to virtually insert the Lombardi trophy inside of the University Laval's coffee table. And so I didn't know the trophy that you get if you win the Super Bowl is the Lombardi trophy. So the more you know. I want to bring your attention on a couple of things. For example, here the reflections and the shadows and the caustics that we barely see in the presentation, but it's great on my monitor. All of those look pretty realistic. So how did we manage to do this? This is a virtual object. We don't have the Lombardi trophy in Canada, I'm sorry. So the way to achieve this is to plant a probe inside of the scene. So here for a probe, we use a 360 camera. And what we do with this, we do an exposure bracketing. So we take multiple pictures with multiple exposures, blend them together with Paul's method, and then this ends up being an HDR map that we can send to any 3D renderer, and then we can obtain the result that we had on last slide. Now the question is, if I am in this scene and slightly change the position where I want to insert my object, for example, now on the table on the right, now, how do I insert an object such that it still looks good? Like all the reflections here, I'm going to put the other image that we had before. All the reflections has shifted. The shadows is not going into the same direction. The caustics has changed slightly also. Why? Because the lighting has changed. We're at a different location in the scene. And In order to do this, we need to take the probe, redo the entire capture, and we need to do this for every position that you want to insert a virtual object or understand the lighting in the scene. Is there a way to do better than this? So turns out we're not the first ones to ask ourselves this question. There's a bunch of people in the literature that has looked into this. For example, Unger et al., who propose a pair of cameras, one that looked at a probe. Here in this case, the probe is a chrome sphere, and the backplate camera is the one taking the actual picture. And you can get great results with this. For example, here, the helicopter has been virtually inserted. The probe that was captured is on the top left, and you can see that as the video goes forward, all the lighting, all the reflections and the shading matches the background image. So this is a very interesting, straightforward way to acquire lighting. However, it's got limited dynamic range, but especially it's pretty expensive. The HDR camera is killing your apparatus cost. There's a couple more methods to do that, for example, using radiance fields. Unfortunately, there's no more cameras that are doing radiance fields because they're all busy dying. Companies doing that are all going bankrupt. But despite this, very unfortunately, I love light fields. Why are they not getting consumer stuff, like consumers excited about this? Anyways, so one way to do this is to take multiple different exposures during your video capture. Another way to do this is to entirely capture the entire bracketing exposure stack for every position that you can find inside of the room. And while those two work pretty well, and especially compared to the previous method, you can interpolate the lightings at any point in the scene. However, in the first case, you've got limited dynamic range, and in the second one, it's pretty slow. It's in the range of a couple of hours to recover just a very small scene, and it can go up really quickly. And the main thing also is this is pretty expensive. How much do you think it costs the capture apparatus that I just showed you in the previous slide costs? It is $200,000. So pretty expensive. The question is, how can we get the best of both worlds? So in this work, what we want is something that is relatively affordable, relatively cheap, easy to use, high quality, and we can recover HDR radiance maps from this. So, so that we can insert virtual objects inside of our scene afterwards. So how do we achieve this? The way that we do this is relatively simple but efficient. We take two 360 cameras. So those are Theta Z1s. Those cameras are readily available. They're out of the shelf. These specific versions are $1,000 each. It is not exactly super cheap, but if you compare it to the $200,000 version that I showed you a couple of slides ago, I think it's much more bearable in terms of cost. And I'm pretty sure it can also be used in much cheaper, with much cheaper cameras. And as you set up those two cameras side by side, you mount them on a monopod, and you ask a wonderful operator to walk around the room relatively slowly, and that's basically it. It takes a couple of minutes, and you get your acquisition. Now, what are those two cameras doing? The first one is busy taking a very regular video. This is a standard video of the person walking in the room. But the second camera is exactly the same setup, but set to an exposure that is as fast as possible. So the image is going to become very, very dark, but you will realize that all the light sources are not saturated anymore. And this is the entire insight of our capture apparatus, is that we split the scene luminance in two, and basically one camera acquires half of the luminance, the other half of the luminance, and then we stitch that together into a 3D representation. Speaking of which, how do we represent the scene in 3D? We're using NURBS. So the way that we use NURBS is slightly different than the original formulation, simply because if you simply take an HDR image and pass it into NURBS, it diverges and completely collapses. So the way that we achieve this is we're basing ourselves off neural exposure fields, which starts with an X, which is a position along a ray. Imagine you have a camera here in the 3D space. You trace a ray that goes through one of the pixels of the image plane, and you accumulate at each position along the array on a position that you call X. You suppose you are at this position, you pass it through an MLP, a multi-layer perceptron, and this perceptron will give you sigma, which is the current density. So am I going through a wall right now or something solid, or am I in free space? So that's sigma, and after that we've got E, which is an exposure. And then this E gets fed to another MLP that outputs color. It receives both the exposure and the position that you are in and the direction, and it outputs color, and it says the color at this specific point in space should be this. And you do this for all the points along the ray, you integrate, and that gives you the color that you should get at this position on the pixel of your image. Now, once you do this for the well-exposed image or the well-exposed sequence, you finish training this, and the stage 2 is to add another one, another MLP that estimates what the dark video is doing, the fast exposure sequence is observing. And then we get those two different neural networks that outputs two different images. How do we reconstruct a full HDR from this? We take the two images that are generated by the two neural networks that I just showed you, and the first thing that we do is that we inverse the camera function. All of those two multi-layer perceptrons output in sRGB color space. We linearize them. We apply a weight. This is just a visibility mask saying that all the observations that are valid is 1 and everything that is saturated is 0. So that's the weight here. And the fast exposure, we multiply it by the exposure factor, so it gets much brighter. Actually, the exact exposure factor coefficient. We sum those together, and we get an HDR environment map. And this is ready to use into any 3D rendering software. You take this and you say, I want to light my environment, my scene, my 3D object with this environment map, and your 3D rendering engine will know what to do with this. So the core idea that I just showed you is pretty simple. The main key thing is that the devil's in the details. There's a lot of details that are important to make sure it's okay before being able to use a result like this. Like, there's a bunch of things that I'm not going to cover. For example, how do we synchronize the sequences together? Really quickly, we just clap in our hands. That's good enough. But I want to talk about self-calibration of the alignment. This is one of the major issues that we had in our pipeline. So the fact that we have two different cameras makes this setup stereoscopic. And unfortunately, those cameras are not exactly at the same location due to the fact that those are two physical components that we cannot embed into one another. And the thing is, we need to understand the distance and the rotation between those two cameras. So what we're doing is that in addition to capturing the regular well-exposed and fast exposure, we restart the apparatus where both of them capture well-exposed, short well-exposed sequence, and then we run it through OpenSFM, which is like ColdMap, but is more readily available for 360 panoramas. That gives us the calibration that we need. And then what we do with this calibration, that gives us the camera to world matrices. We do not have this for the fast exposure. We simply compute the transform between the two in the well-exposed sequence, and we just copy it for the fast exposure. Simple, efficient, it works. Now, if we only do that, this is a global alignment. It's not enough to fix all the, like, light sources sometimes are very, very small, and if you miss it by a couple of pixels, everything is completely misaligned. So we need a fine alignment to fix those cases. So let's suppose we start with a fast exposed image where I see a couple of fluorescent lamps on the ceiling. I go and ask my multi-layer perceptron, my NERF, can you give me the image of the well-exposed image that should be at this location? I get this image. Now the question is, how do we align those two things? We apply contour detection, we binarize those, and then we pass them into contour matching and SIFT matching algorithm, which is the kind of things that happen if all your collaborators did their PhDs before AlexNet was invented. So their solution is like signal processing only. But you know what? It works, so I'm not going to complain. And then we find those matches, and we estimate an homography. We take this homography, we apply it to the fast exposed image. And then now everything has been aligned together. We can now train the second neural network with those aligned images, and things align much better. This brings me to the second contribution of our publication, which is an HDR data set. So we captured 14 scenes. Each of them have 15 ground truth HDR captures throughout each of those scenes. We captured the ground truth using exposure bracketing, and it took us several painful weeks to get everything aligned together and calibrated. So it's now all free for use. Be sure to go to the website. Everything has been already publicly released. So here's a couple of results that we can achieve on the data that I just mentioned. So we can take our method and generate the IBL, the lighting environment that we send to the 3D renderer in order to get some renders. Here are our example renders that we are using for our evaluation. We've got the armadillo, the bunny, and the glass sphere here. Notice how we've got shadows, we've got caustics. All of those effects require HDR to be able to be visible or seen. If I take an LDR image and do exactly the same render, but simply by taking the camera, pressing on record, and getting a regular image out of this, I get this kind of result. No shadows, no caustics, no happiness. So another method proposed to convert the LDR image that I showed in the previous slide to HDR, which does pretty good. A little bit of a color shift here, but it's doing pretty good. Another method is called HDR nerve. It tries to encode directly into the nerve the HDR values. It's slightly dimmer, but it still can perform some kind of high HDR. It's getting some caustics over there. And in comparison, our method is the most faithful of them all. So quick video comparison between those two. Here we're just going through the scene. Our reconstruction in our data set, our reconstruction is much more stable, both in terms of high frequency and in terms of lighting accuracy. So a couple of quantitative results. We benchmark on the LDR render, so we performed a regular render where the image is simply those objects. We compared them against other method that performed the rendering, that performed the lighting that we rendered this object with. The second thing we compared is directly the HDR panoramas that are output by each of these methods. And we encode that in PU21 space so that we can compute PSNR on it. And we also compared directly the HDR renders in linear space on our MSC. And in all of those cases, our method exhibits state-of-the-art accuracy. So we also performed a quick experiment to showcase the impact of the fine alignment. If we do the fine alignment, you can see that all the lights, especially the ones that are further away, are much more aligned, much more precise than if we do not do the fine alignment that I just mentioned to you. Another thing that we did is experiment with Gaussian splats. So we replaced the nerve with the Gaussian splats, and we did something very, very similar to the nerve. We created basically two different sets of parameters for the spherical harmonics coefficient in the Gaussian splats. And the first one represents the well exposed, and the second set of RGB values represent the fast exposure. So by doing this, we can obtain very, very similar results. We found that in our test, nerves perform slightly, ever so slightly better, but both are working pretty well. And our method is not without limitations. For example, we have a fixed dynamic range that is limited by the actual camera setup. So since we're simply taking the fastest exposure of the camera, that means that there are some examples where we cannot simply capture the intensity. For example, here we've got windows that are looking outdoors. Outdoors is very bright, especially if you have the sun inside of your field of view. So the missing dynamic range explains the artifacts that we're seeing here. And then also sometimes the fine alignment can fail. Sometimes it can lead to floaters, and we leave fixing those as future work. So with this, I want to conclude by saying that we've got two main contributions. The first one is an affordable method to capture HDR 3D scenes, and the second one is a data set of 14 indoor scenes with a total of 200 ground truth probes, and I hope this is going to be useful for the community. Thank you so much, and I'm ready to take questions.
Thank you. Very nice job. So
Thank you.
Open for questions over there.
Thank you for the talk. It was wonderful. I had a question about the exposure that you're setting.
Yep.
So is it possible, you only have like basically two settings for the exposure. Is it
Right.
possible to have a range of exposures and have the exposure be a parameter for the neural network instead of having like two networks that predict the exposures?
That is a good question. We have not tried this. In theory, we could adapt the system to do this. We would need to perform the experiments. Unfortunately, I do not have I did not do the experiment that you just mentioned.
Thank you so much.
Any more questions from the audience? Actually, I'm curious, like about
Go ahead.
what if you have like both the motion blur entangled with like sudden lighting change together?
Sudden motion and
Motion
light.
and lighting.
Oh, so we suppose that the capture environment is entirely static in our case. So we have the same limitations as neural exposure fields and neural reflectance fields. So the current method that I just proposed will definitely not work. You're going to have like floaters and shadows instead of the dynamic objects that you have. We could think of extending using a dynamics-aware version of NERF, but that is left for future work.
Sounds good. Okay, well,
you again
let's
so
send the
much.
speaker again. Thank you so much.